Welcome to the talk. My name is Chang'er Lee, and I'm going to talk about handling LP rounding for hierarchical clustering and fitting distances by Ultrametrics. This is joint work with Hyung-Chan An, Mongzhen Kao, and Muting Lee. In this paper, we mainly consider the hierarchical correlation clustering problem, or in short, HCC. For the problem, we're given L layers of complete graphs on the same vertex set, where each vertex or each edge is labeled either plus or minus. We are also given a weight for each layer, and the problem asks to find the clustering for each layer such that the clustering in the lower layer subdivides the clustering in the higher layer. We call these constraints as hierarchical constraints. Note that these clusterings shown here satisfy the constraints. On the other hand, these clusterings don't. We say clusterings are hierarchical if they satisfy the hierarchical constraints. The goal of the problem is to minimize the sum over all layers of each layer weight multiplied by the number of disagreements in that layer. So what is a disagreement? We say an edge is a disagreement if it is a plus edge and its endpoints are separated, or it is a minus edge and its endpoints are clustered. So at layer 3, you can see that there are 2 plus edges and 1 minus edge that are disagreements. For each layer, you can see that the number of disagreements is as such, and the total cost is computed by the weighted sum of the number of disagreements. One reason this problem is interesting is that it is a hierarchical generalization of the classical correlation clustering problem, which has been extensively studied. But furthermore, it has another interesting aspect, which is it generalizes the problem called L1 ultrametric fitting. This has already been observed in the existing literature. So what is ultrametric fitting? The problem is easy to state. Given a distance function d, we want to find an ultrametric t that best fits the given distance function d. An ultrametric is a special case of a tree metric in which all leaves correspond to points and all root to leaf paths have equal length. It has been studied intensively since 1960s across various fields, especially in computational biology. The problem is also known as numerical taxonomy or phylogenetic reconstruction. Here we focus on the L1 and L0 objectives, where the goal is to minimize L1 and L0 distances respectively from the given distance function d. Recall that L1 case is a special case of hierarchical correlation clustering. L0 ultrametric fitting is not exactly a special case of HCC, but still, it is another hierarchical variant of correlation clustering. Here's a brief summary of previous results on L1 ultrametric fitting and hierarchical correlation clustering. The problem is apex hard, and for the algorithmic results, Harp, Cannon, and McGregor in 2005 gave 2 algorithms whose approximation ratios are n and big O of k log n, where k is the number of distances in the input distance function t. Ilon and Charkov in 2005 also gave 2 approximation algorithms whose ratios are k plus 2 and big O of log n log n. Koenada, Das, Kyprides, Parsidis, and Thorab gave the first constant approximation algorithm for the hierarchical correlation clustering problem. Our result is to give an algorithm whose approximation ratio for hierarchical correlation clustering is less than 26. Here's a brief summary of previous results on L0 ultrametric fitting. The problem is also apex hard. Koenada, Fan, Lee, and Mesme in 2092 gave the first constant approximation algorithm. And 2024, Charkar and Gao gave 5 approximation algorithms for the problem. We give a simple deterministic algorithm whose approximation ratio is also 5. Now let me show you our approximation algorithm for hierarchical correlation clustering. Our algorithm is LP rounding algorithm, and we solve the standard LP. In this LP, there are distance variables denoted by x super t sub ij for all edge ij and layer t. The distance being 1 indicates I and j are separated at the corresponding layer, and being 0 indicates I and j are clustered at the corresponding layer. Using these variables, we can write the objective as follows. Recall the definition of a disagreement. If ij is a plus edge and I and j are separated, then there was a disagreement. Therefore, fractional cost incurred by plus edges equals the distance. If ij is a minus edge and I and j are clustered, then there was a disagreement. So fractional cost incurred by minus edges equals the 1 minus distance. So this is our objective. For the constraints, it basically says X is a metric for each layer, which implies X forms a clustering for each layer, and X is monotone, which implies X satisfies the hierarchical constraints. Now let us fix an optimal LP solution and denote it by X tilde. And let us define the distance of edge ij at layer T to be X tilde super T sub ij. There's a useful property stating that the weighted sum of the number of minus edges whose distance at that layer is strictly less than 1 is bounded by the LP optimum. Essentially, this lemma is saying that we can ignore or disregard minus edges with distance less than 1 in each layer, and that only incurs an additive factor of 1 in our final approximation ratio. This can be easily proved by applying complementary slackness and weak duality. Now, let me give you the high-level overview of our algorithm. Our algorithm works in a bottom-up manner. At each layer, we first construct a partition, script Q, which we call a pre-clustering. And based on the pre-clustering script Q, we construct a clustering denoted by script P by merging clusters in the layer below. So let me first explain the constructing part of a pre-clustering. Starting from a trivial partition, we pick a part whose diameter is large, and we split it into two so that the number of edges separated by the split whose distance is less than 1 is small. And we do this until there is no such part whose diameter is large. At the end of the construction of the pre-clustering, we know for sure that each pre-cluster in the pre-clustering has a small diameter. We call this small diameter property of pre-clusters. Moreover, we also know that there are only a few number of edges separated by the pre-clustering whose distance is less than 1, and we call this few separated edge property of pre-clustering. We now see how to construct a clustering. Suppose we are constructing a clustering at layer T. For each pre-cluster Q, we do the following. We find all clusters at the layer below which satisfy certain conditions. Let me defer what certain conditions are to later. For example, let's assume that these three clusters at layer T-1 satisfy the conditions. We merge these clusters into one cluster, say P, and we add P to the cluster. Here we say the current Q, precluster Q, is the gluing precluster of P. We do this by iterating all preclusters in the preclustering, and there might be some unmarked clusters remaining. We just add it to the solution. That's it. Now let me explain what certain conditions are. Roughly speaking, the conditions state that most points in the cluster P prime at layer T-1 are in the intersection of P prime and Q. And from this, we can say that most points in each cluster P are in the intersection of P and the gluing precluster of P. We call this concentration property of clusters. To sum up, we have three properties: small diameter property of preclusters, few separated edge property of preclustering, and concentration property of clusters. Now let me give you a brief overview of our analysis. Our goal is to, the goal of our analysis is to utilize the few separated edge property. In other words, we bound the number of disagreements in terms of the number of edges separated by the preclustering whose distance is less than 1. Let us fix a layer and omit the superscript. Consider counting the number of minus edges clustered together in the clustering, or minus edges, which is disagreement. We first classify it into two based on the distance, whether the distance is less than 1 or equals 1. Recall the definition of the distance above. And also recall that due to our useful lemma, we could disregard minus edges whose distance is less than 1. So we focus on the second type. For the second type, we can rewrite it by the summation over all cluster P in the clustering of the number of minus edges clustered in the cluster P whose distance is 1. And we focus on a single cluster P. We further classify based on its relation with the gluing precluster of P, whether it is clustered in the gluing precluster of P or clustered in P minus gluing precluster of P, or separated by the gluing precluster of P. Note that the first type is not possible since we cannot have an edge with distance 1 in the precluster due to the small diameter property. So we focus on the second and the third type. We give a trivial upper bound by considering all edges with any distance instead of minus edges with distance 1, which can be written as such. And note that the number of the second and the third type of edges are dominated by the third type of edges due to the concentration property. So we focus on the third type, or focus on bounding the third type. By further exploiting the concentration property, we could show that most of edges with this type have distance less than 1. For technical reason, we use this equation as a final bound where gluing precluster is replaced by the whole preclustering. Recall that we started from bounding the number of minus edges clustered in a single cluster P whose distance is 1, and we conclude that it is bounded by some constant times the number of edges clustered in P separated by the preclustering whose distance is less than 1. By summing over all clusters, we can charge the disagreements that are minus edges whose distance is 1 to some subset of edges separated by the preclustering whose distance is less than 1. Similar bounds can be achieved for plus edges that are disagreements. So we can charge it to some subset of edges separated by the preclustering whose distance is less than 1 And note that the charged subset of edges for each type of disagreements don't overlap. Therefore, in total, disagreements other than minus edges whose distance is less than 1 is bounded by some constant times the number of edges separated by the pre-clustering whose distance is less than 1. And due to the few separated edge property, the number of edges separated by the pre-clustering whose distance is less than 1 is bounded by the constant times the LP value of the corresponding layer. And by doing the weighted sum over all layers and applying our useful lemma, which incurs an additive factor of 1, we can show that our algorithm is a constant approximation ratio. With more delicate analysis, we can show that it has an approximation ratio less than 26. We conclude this talk by presenting our algorithm for L0 ultrametric fitting. It's again LP rounding algorithm, so it first solves an LP, here the standard LP. We go top-down manner, and whenever a cluster has a large diameter, we just split it as we did in HCC. And that's it. Using the L0 ultrametric fitting version of useful lemma, we can show that this algorithm is 5 approximation. That concludes the talk. If you're interested, please check our paper. Thank you for listening.